Hi everyone. This is a lesson on optimization, which is actually a really interesting part of calculus, and it is to do with real-world max-min problems, where we're trying to maximize or minimize something in the real world. And as you know, in the real world, there are always constraints. So these are problems where we're trying to optimize something. In other words, within the constraints, we are trying to do our best. That's really what it means with the word optimize. There's something that needs to be maximized or minimized, but there's a constraint, and so how can we do our best? That's the idea behind all of these problems. So the first one says a farmer has 1,000 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So just like with our related rates problems, we're going to start by drawing a picture. So for this problem, I draw the river, and then I would imagine the farmer is putting his fence. He said he needs to have a rectangle, so it's something like this, and it borders the river, so he doesn't need a fence along the river. And we are thinking of the dimensions, so I would give the dimensions variable names, and we're also dealing with area, so I would give the area a variable name. That would be my first step. My second step is going to be to write an equation for the area, so for the quantity that we're trying to optimize, because it says, what are the dimensions of the field that has the largest area, right? So we're trying to maximize the area, and I know a formula for the area is x times y. Now, we are in the real world, so these problems will always have a constraint. The constraint here is that we only have 1,000 feet of fencing. So in other words, 2x, because there's two sides, which are x, plus y is equal to 1,000. This is a formula coming from the constraint, and I kind of call this a helping formula in that it's going to help you rewrite the optimization formula using only one variable. So in this case, I can eliminate y from my a formula by saying, well, y has to be 1,000 minus 2x. And so then the area formula becomes a is equal to x times 1,000 minus 2x. So the area is now negative 2x squared plus 1,000x. So that's my area formula as a function of x. Now, you can already see that that's a parabola, so let me just go off to the side here and say if a is equal to negative 2x squared plus 1,000x, we actually don't need calculus to do this particular problem because we can recognize that this is just a parabola, and it has its axis of symmetry at negative b over 2a, or 250, and at that x value, the area comes out to be 125,000 if you just put back 250 into the area formula, right? So I can already do this problem actually without calculus and realize that the area is a parabola, and I want to be at the vertex to maximize it. But how do we do this with calculus? Well, we're going to use our absolute maximum and minimum, or local maximum and minimum ideas that we developed in the last few lessons to get the answer. So we'll go to step 3, which is going to be to find the derivative of the thing that we're trying to optimize. Oh, actually, that will be step 4. Step 3 is we do want to think about the domain. Some of these problems will have a closed domain and some of them will have an open domain. So we're going to think about that. In this problem, you could imagine that x can be 0. If x is 0, then, the farmer has basically laid all of his fencing just along the river, which would be kind of silly, but it's possible, right? Or the other situation would be if y is 0, and that would be when the farmer has laid his fencing just in two strips like this, 500 and 500 on top of each other, right? So both of these cases are possible. They'd be silly, but they're mathematically possible. If you look at the area formula, we're saying that we can put in x is equal to 0 into that formula. It wouldn't make sense for the area to become negative, right? So basically, the maximum x we can put in is here. The minimum x is here. X equals 0 is the minimum. X equals 500 is the maximum. So the domain of this function is 0 to 500. And I can now make the candidates table because I have a closed domain and a continuous function. So I can go, step 4 is my candidates table with x and a of x. The quantity that you are trying to optimize, which is a, right? That's what should go in the right side of this table. So then we have 0 and 500 as the endpoints. We're going to take a derivative and set it equal to 0 to find the critical point. So we do a prime, which is equal to negative 4x plus 1,000. Set that equal to 0 and get that negative 4x equals negative 1,000, x equals 250. So that goes here as a critical point. We already know the area is 0 for my two silly cases. And when x is equal to 250, the area will be 250 times 1,000 minus 2 times 250, or 500. So this will come out to be 250 times 500, or 125,000, okay? So that is clearly going to be my maximized area right here, okay? So we can end the problem by saying that the farmer can maximize his field area by choosing a field with length equal to 500 and width equal to 250 feet. Okay, so that's our first example. Okay, our second example is a cylinder. Should be example 2. It's going to be a cylindrical can is manufactured to hold 1 liter of oil. Find the dimensions of the can that will minimize the cost of the metal to manufacture the can. So we have a can, it's a cylinder. So this is step 1, draw the picture and label it with variable names. So we can put R and H as our variable names. We know that we're going to be dealing with volume, so we can say V is going to be the volume. We also know that here we have the cost. What we're trying to optimize is the cost. The cost is typically the cost per square meter of metal times the area of the can, right? So really what we need to minimize is the surface area of the can, right? Surface area of the can. Make sure that when you give variable names, you don't say SA. We want just one letter. So S is going to be my surface area. Okay, so then step 2 is to think about the optimization equation. That is S is going to be equal to the two, the top and the bottom of the can. Those would be pi r squared and another pi r squared, so 2 pi r squared. And then the curved surface area of the can is 2 pi r h. So my total surface area of the can is 2 pi r squared plus 2 pi r h. Let's think about our helping formula coming from the constraint. That's going to be the volume. The volume is 1 liter. I'm going to use 1,000 milliliters for this. So pi r squared h, which is the volume of a cylinder, has to be 1,000. And using this, I can say h is equal to 1,000 divided by pi r squared. So now I can go back into that surface area formula and rewrite it by eliminating one of the variables. I'll choose to eliminate h in this case. And so I get 2 pi r squared plus, I can just cancel some things and get 2,000 divided by r. Okay. So now I have this optimization equation. S is equal to 2 pi r squared plus 2,000 divided by r. 2000 divided by r means I cannot put 0. 0 is an excluded value, right? So this is a problem which does not have a closed domain. So when I think of my domain is going to be r greater than 0. It can technically go up to any number, but it has to be greater than 0. So I'm going to need to, I cannot use my closed interval test. I'm going to be using the first derivative test to figure out the minimized surface area. So then step 4, I'm going to find the first derivative. So s prime is equal to 4 pi r minus 2000 over r squared. This 2000 over r, we're going to think of it as 2000 times r to the negative 1 when we differentiate. So that is s prime. I'm going to find my critical points by setting s prime equal to 0. So I get 2000 divided by r squared equals 4 pi r. Cross multiply, 2000 equals 4 pi r cubed. R cubed is equal to 2000 divided by 4 pi, or 500 over pi. So r is the cube root of 500 over pi. That is a decimal number. We can leave it like this for our answer. So r is equal to cube root of 500 over pi is my critical point. So let's think about this now on our number line. So if we've got the critical point right there, we need to think about s prime and make sure that this really is a minimum. So let's think about that. Okay, so something that we sometimes have to do is estimate a number without a calculator, right? So here we have 500 divided by pi and the cube root of that. That's the exact number, right? So the approximate number we would think maybe, well, 500 divided by 3, that is 166-ish, right? So we're really talking about something like the cube root of 166. Well, we know that the cube root of 125 is 5, and the cube root of 216 is 6. So this is somewhere between 5 and 6, right? So, and I know I've made some other estimates up here. I didn't do all of this exactly, right? But it would be safe to say 10 is certainly a number greater than this cube root of 500 over pi. Similarly, 1 is certainly a number less than that, right? So then you can use those as your test points, and you can say s prime of 1, s prime was equal to 4 pi r minus 2000 over r squared, so 4 pi minus 2000 over 1, right? 4 pi times 1 over minus 2000 over 1. This is definitely less than 0. So s prime is negative on that side. S prime of 10, 4 pi times 10 minus 2000 divided by 10 squared. This is 40 pi minus 20, right? That's definitely greater than 0, right? So we've established that there is a sign change of s prime at the cube root of 500 over pi, and s, therefore, is decreasing and then increasing. There is only one critical point, so this I'm going to remind you off to the side, only one critical point, right? And so we can be sure that this r is equal to cube root of 500 over pi is definitely a local min, because s prime changes from positive to negative, but it's not just a local min, it is also, and it's an absolute min, right? The absolute min, because it is the only critical point on the domain. So we have a situation where something, which is in this case s, is decreasing, and then it is increasing. And it's always decreasing to the left of this number, always increasing to the right. So it must reach its lowest point at r equals the cube root of 500 over pi. So that's the answer. Let's think about the h at that specific place, right? So h, if we go back up here, we said h was 1000 divided by pi r squared. So then h for this particular r is 1000 divided by pi cube root of 500 over pi squared, right? And so we can simplify this a little by just putting into rational exponent form. So it's pi times 500 to the 2/3 over pi to the 2/3. And then this is like pi to the 1 divided by pi to the 2/3. So I'll get pi to the 1/3 there. On the top, I have 1000, which is 2 times 500 over 500 to the 2/3. So I'm going to get 2 times 500 to the 1/3, subtracting 1 minus 2/3 over pi to the 1/3. So it's 2 times the cube root of 500 over pi, right? Which was my earlier number. That was the radius number, right? So this right here is the r that we're evaluating all of this at. So in other words, a can where the height is equal to twice the radius, right? So the height is equal to this, and the radius is equal to this. This can, right, is going to maximize our, minimize our surface area while keeping our volume at 1 liter, okay? So this is how you would do a problem where you're not on a closed domain. Okay, let's do number 3. A box with an open top is to be constructed from a standard 8.5 by 11 piece of paper by cutting out a square from each of the 4 corners and folding up the sides. Find the largest volume of box that can be constructed. So we've got an 8.5 by 11 piece of paper. This is my step 1, the picture. I know I'm cutting a square out of each of the corners, and I can give the square side the name X. I know that I'm dealing with the volume, so the volume of my box, I'm going to call it V. Okay, so then step 2 will be to write an equation for V. In general, V is going to be length times width times height. I'm going to use the geometry of the situation to realize that the height will be X. So I have L, W, and X. L and W are not names that I have in my picture. I have to get rid of them. And I'll get rid of them by realizing that L is equal to 11 minus 2x, and W is equal to 8.5 minus 2x. And what we're saying there is that this width of the box will be equal to 8.5 minus 2x. And the length of the box, right, will be 8.5. 11 minus 2x, right? So this is 11 minus 2x, and this is 8.5 minus 2x, okay? So now I can just rewrite this whole equation as 11 minus 2x times 8.5 minus 2x times x. That's my volume equation. If you just expand that out, you're going to get 4x cubed minus 39x squared plus 93.5x, okay? So that's our equation that we need to optimize. Step 3 is the domain, right? You can realize the domain, it can be 0. You'd have no box, but technically you can put x equals 0 works in this equation. The biggest domain that makes sense is 4.25, right? Because if you make a box which is 4.25, you'd be cutting off half of your 8.5 square here. 8.5 width here, and so you'd have a situation like that, right? You'd have no box, but we can use it in the equation, so that's our domain. Step 4 will be our derivative, which is 12x squared minus 78x plus 93.5. Then we're going to set that equal to 0 and use our quadratic formula because it's not factorable to solve. So we get x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So practice getting these numbers into your calculator and getting out the two roots, 4.9145 and 1.5854, right? These are going to be my two roots. I do not have to worry about this guy, this critical point, because it's not in the domain from 0 to 4.25. I'll only worry about the 1.5854. So I make my candidates table, 0, 4.25 are my endpoints, 1.5854 is my critical point, and I will calculate the volume, which is the equation, 11 minus 2x times 8.5 minus 2x times x. I'll do that for each of these values. I know that on the ends, I basically don't have a box, so those are 0 volume. And if I use 1.5854 for x, then you're going to find this number is 66.1482, right? Keep everything to 4 decimal places for calculator problems. So there we go. That's basically the biggest box that you can make would be when the square side is 1.5854 inches, and the volume at that time would, or that particular dimension would be 66.142 cubic inches.